Go ahead.
Good morning, esteemed panelists, members of the audience. We are AEOS Enterprises. Behind me I have Richard Garcia, Natalie Jackers, Dana Felberg, Stephanie Frederick, and Cheyenne Baltonado. Richard will be taking the introduction of our project.
Thank you, Ryan. I'd like to say I'll talk about the responsibilities for this slide. First we have Ryan Bishop, who is our detail staff sergeant. Then next we have Cheyenne Baltonado, who is our safety personnel. Then we have Natalie Jackers, our sub-collector, who's collected all data for that, and region tester. Then we have Dana Ferber, who's our engine operator and the engineer of the engine. So that's what we worked on. And finally me, I worked with the lift generator and the engine. So and then Stephanie Frederick worked on the instrumentation of the project and the regenerator. Next slide, please. Project requirements since prelim. We must make a desktop size computer size almost, or something like that. Must operate in a cycle. Must operate in a cycle and must produce the 100 watts of power. And must be instrumented to measure different temperatures at different locations and pressure at one distinct location. Must be the workroom must be safe, so it means not toxic, not flammable, not corrosive, and must be fitted for it must be under a budget of $1,000. Next slide. I'll give a quick system overview of how the engine is supposed to work. Not going to go over behind. We need minimum 100 watts, so we need 100 watts from the earth generator since that is the last component. So we say we need 100 watts. Now, next, according to its efficiency of 0.9%, we need 111 watts per 111.1 watt for the certain engine. Now we use certain efficiency of close to 20%, and from there we need close to 404 watts. So we need a final efficiency of 0.70, which goes 600 watts on the surface of her known lens. Next is Natalie Jackers, and she's talking about our collection.
Thank you, Richard. At the beginning of detail, our team acquired a solar collector. The solar collector we have used is a spot for no lens that has a focal length of about 1 meter, can reach maximum temperatures of 1100 degrees Celsius, and has a surface area of 1.35 meters squared. As stated by Richard on the previous slide, we need a minimum heat rate of 600 watts to produce a net output of 100 watts from the generator. Because there is an average heat rate of about 100 watts per meter squared on the surface of the earth at any given second, we can expect to get a maximum heat rate out of our solar collector of 1,350 watts. Looking closer at the expected value for the heat rate in to our system, on this given day at this approximate given time, at the location of Embry-Riddle where we are right now, if we take our solar collector outside and we move it to 23 degrees from the vertical and then rotate it 147 degrees clockwise from north, we can expect to see a maximum value of 900 watts that will exit the lens after our losses. Taking calculations and going further into actual testing, the team took the spot from our lens outside to melt some pennies. The pennies that we had melted were minted after 1982, which is important because it is mostly comprised of zinc, meaning the maximum temperature that the team could reach with our solar collector is only about 420 degrees Celsius, which happened in approximately 30 seconds. Thank you. Our second testing sample was with steel samples that were put into the contraption that you see here. The steel sample is hooked up to a thermocouple that is tapped into the inner core of our steel sample. The problem with our testing here is that everything was very inconclusive, but we were able to reach temperatures of at over talking about the Sterling engine.
Thank you, Natalie. I will begin a discussion of our Sterling engine subsystem with an engine overview. So as Richard stated in the introduction, we are using a Sterling engine in our system. More specifically, this is a 90-degree offset V-twin alpha-type Sterling engine. This engine operates by expanding and contracting a fixed volume of working fluid using a temperature differential in between the two pistons. This is a closed system external combustion without a phase change, so there's no intake or exhaust. The lack of phase change aids in the use of a lower temperature heat source, such as the Fresnel lens that we are using. For this engine, there are 4 strokes per cycle. Those strokes are expansion, hot transfer, contraction, and cold transfer. These 2 images depict the major components and layout of the Sterling engine. So attached to the expansion piston is a heater, and attached to the compression piston is a cooler. These 2 pistons and piston heads are connected via a transfer passage which contains the regenerator. The final primary component of the Sterling engine is the crankshaft connected to the flywheel. The crankshaft allows for the linear motion of the pistons to be converted into rotational motion of the flywheel. I'll now discuss the cooler component of our Sterling engine. The overarching design goal of the cooler is to most effectively reject heat from the cylinder. In order to accomplish this, the cooler must be made out of material with a high thermal conductivity. Additionally, in our design, we must work to maximize the wetted area of the cylinder chamber while simultaneously minimizing the void volume. Finally, we must outfit our cooler with instrumentation so that the team can realize the operating parameters of both our cooler and our engine as a whole. Throughout the course of this semester, we established 3 distinct cooler designs, as seen on the slide above. We have our prelim cooler design, and this is the cooler that we spent last semester designing as part of our preliminary design course. We also have fabricated coolers versions 1 and 2. Our prelim cooler design, actually shown here, was printed out of ABS P430 plastic with our 3D printers. It is 5 inches in diameter. It has a 1-inch thick base and 1-inch tall cooling fins. It also has annular cooling fins along the base for additional cooling. This design also has a hemispherical chamber with 2 distinct ports. The larger port is for our transfer passage connection, and the smaller port is for our thermocouple instrumentations. The major benefits of this design are its incredibly precise specifications as well as the optimized cooling fins. We did spend an entire semester working to optimize this design for as much cooling as possible. Unfortunately, the major drawback of this design was we were not able to test it. Due to fabrication constraints, such as lack of trained personnel to operate our machine shop equipment, as well as our budgetary restraints, and the personal limitations we face as students attempting to hand machine complex geometries, we were not able to create this out of aluminum as originally intended. So we were not able to test it because the plastic would have melted. We also made our fabricated cooler version 1. This was made out of aluminum 6061, as shown here. It is 5 inches in diameter, and it is actually 2 components. So we have the top plate, which is a 1/2 inch plate of aluminum, and then the base is 1 inch thick with a 2.5 inch diameter hole bored out of the center, giving it a donut shape. So these 2 components fit together and then bolt on top of the compression piston. There's also a transfer passage from the side. The primary benefit of this design is it is made out of the correct material, so we were able to test it on our engine. We will discuss that testing a little bit more later. Also, the side transfer passage allows for maximum cooling surface area on the top of our cooler. The major drawback to this design is the immense void volume, almost 6 cubic inches. Void volume is negative because it significantly decreases the efficiency of our engine. Additionally, there's a distinct lack of cooling fins and overall design optimization on this cooler. That shortcoming stems from the fact that this design is driven solely based on manufacturability. When we were not able to create the cooler that we had liked to, we needed to regroup and develop a cooler design that we would be able to manufacture with the resources available to us. And finally, we have our fabricated cooler version 2. This is actually up here on our engine right now. It's made out of aluminum and it is 5 inches in diameter. It is 1/2 inch thick, and the transfer passage comes from the top rather than the side. The primary positive aspect of this design is its essentially negligible void volume. Because there is no chamber, there is no excess chamber volume. Like the version 1, there is no design optimization, unfortunately, no cooling fins, no specialized cooling features. The top transfer passage eliminates some cooling area, making it less effective. Now, Richard Garcia will discuss the heater components.
Thank you, Damon. So we have a heater. Our initial designs for the heater must effectively receive and transfer heat to the extended cylinder of the heater head. The material must have a high thermal conductivity, must maximize the wet area on the cylinder chamber, must minimize the bulk volume in the cylinder chamber to make it more efficient, must minimize conductivity losses to the environment, and must be fitted for instrumentation. These are three designs we made. Like Liam said, the first design on the left, for our left, we see we made that inner freedom, where we spend a lot of time on making sure that the heat will stay inside the steel head and transfer down to the piston. Next is the two fabricated heater heads we made this semester. First one is made of AEOS P430 plastic. It's 4.75 inches in diameter. Thickness is 1 inch, and a volume of 1.605 inches cubed. The negatives about this, if you're not able to test this, is made out of plastic. And we have fabrication constraints on the heater head. The positives are we optimize the design with thermal wells onto the heater head, minimize the volume in the heater head, and it's outfitted for instrumentation. And next one is the first version we made of in ASFAB. The material is made from 1018 cold steel. It's 5 inches diameter, and the thickness of 0.5 inches, and the chamber volume of 4.91 inches cubed, which is starting with negatives. The volume is too big where the efficiency goes down, and the lack of design optimization on the cylinder head is a bad part. The positives about this heater head, version 1 we made, it's a side fitting for a transfer passage. It was fitted for instrumentation and sufficient for service heating area, but the service it was able to have should be sufficient enough to add seal. Version 2 of our heater head, also made from 1018 cold steel, 5 inches diameter. It's 5.5 inch in thickness, and its chamber volume is nearly 0 since neutral pressure for the transfer exchange. Then the positive about this is minimal oil volumes is nearly 0, and faster transfer throughout the heater head. Negative spots, there's no room for tap heating on the heater head. Cannot be instrumented for temperatures or pressures. Lack of design optimization, and surface was not sufficient enough for seal on the heater head. Next is safety infections with trash passage from generator.
Thank you, Richard. As mentioned previously, the generator is located in between the hot cylinder head and the cold cylinder head. The purpose of the generator is to increase efficiency by storing thermal energy. It does this by maintaining a temperature in between the temperature of our hot cylinder head and the temperature of our cold cylinder head. Because the generator is at that median temperature, it has the effect of pre-cooling the air, leaving the hot cylinder, going to the cold cylinder, but also to be able to preheat the air going from the cold cylinder into the hot cylinder. And because you spend less energy, because the temperature difference is less between because the air is preheated because of the generator, you get better efficiency because there's a lower temperature. There are several different designs that we can have for our generator. The generator is comprised of a 1/2 inch diameter aluminum tube and also a steel coil inside. The designs that we tested for our coil was a conventional coil, which is wrapped up similar to how you would fold a piece of paper. So it's rolled up in a fairly standard fashion like this and then inserted into the aluminum tube. The other option was a spiral coil, and we folded it back and forth similar to I used to make a paper fan, but then it was rolled into a coil and then inserted into our aluminum tube. The thought here was that if we had more surface area, we'd be able to better transfer the heat. Moving forward, we wanted to test the steady state temperature and how long it got there, how long it took to achieve that temperature, but also we wanted to test the cooling of our generator. In order to establish a baseline, we heated up the generator and then just let it cool off with room temperature air. And we also heated the generator and then passed cold air through going the opposite way to test the cooling there. So the way we performed the testing was we had our generator and we used a heat gun to send hot air through. This test was done with our conventional coil, so we had a heat gun to send hot air through one side, and we inserted a thermocouple on this side to measure the temperature. We found that our second test took less time to achieve our steady state temperature than the first test, but this was due to having a higher starting temperature because it was the second time that we were heating the same coil, so we started at higher temperature. But we found that it was more important to start at the same high temperature if we're measuring cooling, and we didn't care as much about the time it took to get there. We also saw the orange line from the second test drop significantly compared to the blue line, and that's what you'd expect when you pass cold air through versus just letting it cool off compared to the atmosphere. We found, because we had inserted the thermocouple into the side of our coil, we found that it was in contact with the coil itself and with possibly the inside wall of our aluminum transfer passage. And we really wanted to measure the temperature of the air that was going through our generator. So in order to do this, we decided that we needed to set up a thermocouple on both ends, at each end, so we could measure the temperature of the air going into and also leaving our generator. So for our second test, we gathered fresh data to be able to measure the temperature of the air and also to measure it at each side. We saw that the average high temperature was, our steady state temperature was about 700 degrees, whereas the temperature on the cold side was about 200 degrees. So that gave us about a 500 degree difference with drop across the generator. And now Dana will talk about our complete engine.
Thank you, Stephanie. So now that we have discussed all the individual components of the engine, we can see how the different engine iterations all integrate. So these two pictures depict our complete engine integrated with our preliminary design components attached. This engine is also known as Goldilocks. You can see the cooler with the cooling fins, the heater with the thermal wells on top, and then the transfer passage and regenerator connecting the two. These two images show our completed engine integrated with our fabricated version 1 components. You can see our cooler with our cooler and our heater, and then our transfer passage. And then finally, we have fabricated engine with version 2 components attached. On this, this is actually the same model that is up here right now. So you can see the thinner coolers and the heater, and then the transfer passage in between the two. So now Richard Garcia will discuss the power generation subsystem.
Thank you, Dana. Like I said, we thought that the electric generator, I did test it to that point, and the objective was to get output from the regenerator, the electric generator. It's a Wenzilla 12-volt motor generator, and also DC powered. The point ratio on this on the regenerator, electric generator, is 3:5, and we use a law of power equals current times voltage. We with the testing we got data, and eventually we got to the power curve of what we need to reach to turn on whatever we want to turn on. And this we need around 100, 200, 100 watts. So we assumed around nearly 600, 700 RPMs. And we used a multimeter and tachometer to do these tests. Next is state pressure system integration.
Our solar thermal rig is divided into 3 subsections. The solar section, which is primarily comprised of our Fresnel lens, the engine subsection, which is the heater head, cooler head, flywheel, and regenerator, which is not pictured here. And the electrical subsystem is mainly the electrical generator. The big picture here is that we wanted the sun to be coming into the lens, and then from the lens it gets focused onto our hot cylinder head. From the hot cylinder head, it gets transferred through the regenerator to the cold cylinder head, and the Stirling cycle transmits the energy to be able to rotate the flywheel. The flywheel is then connected to the electrical generator by our V channel belt, and it has approximately a 3:5 ratio. The power output can then be measured from the electrical generator. It's important to be able to adjust our entire lineup so that it's able to track the sun. And we accomplish this in a couple different ways. First of all, our stand is able to be adjusted for tilt because we want our lens to be perpendicular to the sun. And also we want our engine to be able to be parallel to our lens. So we want them both to be able to move together. As you see in the picture here, the stand is adjustable for both tilt and height, as well as the mount that our table that we've got to mount the engine to is also tilt adjustable. So we can make sure we have the proper alignment between everything. We also needed to be able to make sure that the belt between our flywheel and the generator is tensioned appropriately. So we have an adjustable boundary to be able to make sure it has the proper tension. And now Cheyenne will talk about our safety considerations.
So a big part of the detailed design class is completing testing, and with that comes safety considerations. So the team looked at how to keep the operator safe during the testing process, how to maintain a safe environment for those observing the testing, and then also how to preserve the one-of-a-kind hardware, which is our solar thermal rig as a whole. Before identifying each hazard, we needed to be able to categorize the hazards, so we developed a risk matrix. This displays the probability of the hazard occurring and then also the severity of the hazard. It should be noted that when you analyze any given hazard, the severity can never be lowered with the appropriate safety precautions, but the probability of it occurring can. So in the following tables that you will see, there is an initial risk classification for each hazard, and then there is also a mitigated probability risk for it. So on the right-hand side of this slide, you can see a graphic depicting where each operator is to be positioned during the testing process. And the table on the left-hand side displays the possible issues for operators A through C. I just wanted to highlight operator A's possible issue as a potential fire that may occur from the system, and the safety solution is listed next to it. The initial risk classification is in the red category, which would call for the team to have an immediate shutdown of the system. With the appropriate safety precautions taken, that risk can be lowered from the red category to the yellow, which is acceptable to the team after review. Again, there is the safety graphic depicted on the right-hand side, and on the left-hand side, the table depicts the potential issues for operators D through F. On the right-hand side, I would just like to highlight in that graphic that there is a designated safety area for the observers to maintain, for the operators to maintain during the testing process as well. Lastly, these two tables display all the hazards that we have identified in respect to the observers, operators, and also the one-of-a-kind hardware that we are testing. On the left-hand side, in the last row, you see the possible fire again listed. These are the proposed solutions in order to prevent that possible fire from occurring. And again, we're moving from the red category, which is shutdown of the system, to the yellow, which is acceptable. One of the things that we did do is we did make two different covers for the lens. One is to prevent sunlight from hitting the lens, and then there's also additional cover that goes on top of the whole system to prevent it from getting scratched or any abrasions happening to the lens. Lastly, I just wanted to briefly mention that this is our emergency meeting location annotated by the red star in the graphic that you can see. Our testing location is in the yellow box, and the purple pathway is the allocated path that we would take in case of emergency. We selected this area because it's the optimal distance. It's far enough away from the testing site if there is a fire or any potential hazards, but it is close enough that we can easily get there in a timely manner. It's also easily accessible to emergency vehicles should that be necessary. And next is Natalie with system testing.
Thank you, Cheyenne. After observing our safety considerations, the team decided to start begin testing. In the interest of time, weather, and fabrication, the team was only able to implement the Stirling engine with the generator to be tested. Pictured here, you can see our fully integrated system being tested. To heat the heater head, we used a nat gas torch. To cool the cooler head, we used some dry ice in this tin can. And then to start the generator, we used a drill. So next, Brian will play a video that shortly demonstrates the testing of our fully integrated system.
I guess that's not the button to push.
Thank you, Ryan. So during testing, the team decided to take 10 temperature measurements at the given locations above, between the cooler head, the heater head, and the regenerator. On this slide, you can see some initial temperatures that we have taken from the test. It's important to note that the delta T is 235 degrees Celsius between the hot cylinder head and the cold cylinder head. Next is a picture of our final temperatures from the test that we had completed in about 1 minute and 30 seconds. Again, I'd like to denote that there is a temperature difference of 226 degrees Celsius between the heater and the cooler. The data that you have previously seen on the last two slides are all depicted in this chart right here. It is important to denote that the temperature differences between the two heads during the whole system is what drives our system. Also, as you can see, the cooler head has gone up in temperature and the heater head has gone down in temperature. This means that our generator and cooler have been working effectively. During our last testing, we took a thermal imaging picture of the test. As you can see, the heater head is bright white or yellow, and the cooler head is getting to a dark purple. Had we been given optimal conditions and more time, the team would have then took the fully integrated Stirling engine and generator system and then gone outside and tested with the Fresnel lens to do a fully operational Stirling solar thermal grid testing system. Thanks to Brian, and he will be talking about the conclusions.
Thank you, Billy. So throughout this presentation, we've reviewed the key features and testing of our components and subsystems. Those components being the heater, cooler, regenerator, electric generator, and of course our lens, and our entire system of solar thermal grid. We were able to accomplish the majority of the tasks as outlined in our request for proposal. As you can see here, we did not produce a net output of 100 watts. The asterisk next to our instrumentation, it should be noted that we purchased and acquired all of our instrumentation and used it during testing. However, our final iterations of the heater and cooler design did not allow for the implementation of these instruments. The asterisk next to the $1,000 budget will be discussed here in just a moment in the future slide. So as is with most engineering, and I'm pretty sure all of life, our expectations greatly outweigh the realization and the reality of the project. Here is the same infographic that we used earlier. It is acceptable to expect about 1,350 watts of solar energy to be entering the lens. When you follow that through the efficiencies of the lens, you're going to lose that at every point. Now, we used very conservative efficiencies early on for our expectations, but there are a lot of losses that we either didn't expect or couldn't account for early on in our design. The largest loss is between the lens itself and the engine. There are many thermal losses, whether radiative, convective, or conductive, at the heater head. Our design was optimized to address these issues, although because of machining constraints, we were unable to implement this. Next. Earlier, we used a conservative efficiency for the Stirling engine of 20%. This is along the lines of most Stirling engines that are operational nowadays. But considering the level of fabrication technology within the air compressor that we modified into this, it is most likely much more conservative to use 10% instead of 20%. These two losses are two that we did not account for early on in our expectations and calculations. Next, the pulley system, although rather efficient, we do lose 5% through that. Once the pulley's turning the generator, that efficiency remains approximately 90%. But all in all, if we have an approximate 1,350 watts entering the lens, by the time we get out the other end, we have about a third of what we're required to make. This approximate 33 watts of energy is most likely not enough to overcome the friction within the engine, the compression that's caused in the engine while trying to start up. Affects a lot of factors that just won't allow the engine to run. I believe it's kind of a rule of thumb that if you want to make it 100 watts, you've got to plan for 1,000. So through all these successful failures of ours, we came up with a couple recommendations for any future teams that want to stand on our shoulders and try to accomplish this task. The main engineering principle that drove a lot of our design is the unidirectional heat source. Using a Fresnel lens like this, all the heat comes from one direction. The majority of Stirling engines do not heat in this fashion. They heat in an annular fashion around the outside of the cylinder and use a very thin volume between the displacer piston and the cylinder walls to allow for rapid expansion of the working fluid. Because of the spot lens, we were unable to do that, but if someone was to pick up this project where we left off, you could create a chamber around the cylinder and fill it with molten salts such as sodium, and then use an array of mirrors or heliostat to heat from many directions. You would also be able to collect more solar energy because you would be increasing the surface area of collection. As mentioned before, we have about 1.3 square meters. You could greatly increase this using an array of mirrors. Next, we did have a lot of issues with solar tracking. The sun moves about 15 degrees an hour, so that's a quarter degree a minute. It doesn't seem like a lot, but when you're trying to align two components that are on separate bases, it's actually a quite cumbersome task to accomplish. So it is our belief that if a future team was to create a system to either automatically track or at least attach both components to a similar base to make the azimuth adjustments easier, that we would be able to better realize the power of our Fresnel lens. Next, the working fluid we used is air because it's everywhere. The standard working fluid amongst operational Stirling engines today is helium. Helium, however, is a very small molecule, so it likes to leak places and mainly past seals and rings. So this engine itself may not aid itself to running on helium, but using helium in a Stirling engine greatly increases the power output. Also, the base pressure or case pressurization of the engine has a linear effect to power. The more we pressurize the case, the more power we get out of it. If a team was to use this same air compressor pump, the engine itself, the base of the engine, you could optimize the rotating assembly. Internal to that, you have pistons, connecting rods, crankshaft, and bearings. These can all be balanced or even lightened. The loads expected in this Stirling engine are much smaller than that's expected of a compressor, so it's well over-designed for our Stirling engine as far as the rotating assembly goes. So that can be, as I said, lightened, balanced, anything to remove the drag forces within the engine. Also, this is a fresh engine, so it's never been ran as an air compressor, so the rings aren't quite broken and you have excess drag that is experienced within the engine. If a team wants to pick this project up and got this operational, it would be best to actually make use of our electrical power. The values that we measured are instantaneous current and voltage. There's no electrical, so therefore we're not actually producing any power even while spinning with the drill. It's just instantaneous or basically imaginary power without the load. So I believe it would be very good for a future team to make this useful for not only their project, but make it useful for the community, the world. There's a big need for small-scale power generation across the world with like 1.2 billion or 1.2 billion people without access to power throughout their community. Throughout this project, we also realized a couple of constraints that were placed upon us from the university itself, whether intentional or not. Probably not intentional, I would know. Anyways, I feel like it's necessary to ensure the proper support for our students in their endeavors. This project was, our parts themselves, our cooler and our heater, were designed understanding that we have the machinery that can actually machine this. We have the ability to do it as far as machinery go, but in the end, we didn't have the ability as far as personnel go. AXFAB is greatly understaffed for the ambitious tasks that our students are designing, and I feel that the university did let us down just a little bit with this. Next, this is something for me that's pretty personal. I come from a maintenance background. We need to make sure that the environment that our students are in nurtures a practical engineer along with a research engineer. We need the guy that can run all the equations, but we also need the guy that can make it work. For every Hans van Ohain out there, the father of the jet engine, we need a Max Hahn. Max Hahn is who built his engine. We need both of those engineers. Not every one of us can be that complete round engineer that can do both sides of it. We need to make sure that not only are we focusing on how engineering works and how it's great for the world, but how to make it work for the world. Here you can see our budget. As mentioned before, I had an asterisk next to our $1,000 budget constraint. We did go over budget in our total, but it should be noted that because this is the first energy track presentation, the college was gracious enough to purchase some of our equipment to support the development of our energy track program. Those components being our thermocouples, which will be used throughout S&I labs and other projects for capstone, and our Fresnel lens. Everything else was purchased throughout the student budget, and that value was well under $1,000, so I feel we met that. But we did spend more than our $1,000 budget in the end. We had an expected labor rate or completion of about 1,100 hours in the end. We reached 96.1% of this. You can see a lot of that was in the last week. There was a lot of time put into testing and preparation for this, and I would really like to commend my team for pulling it together in the end. Maybe I shouldn't tell you this, but Monday we didn't have any. Well, not literally. Figuratively. It's like, this completes our presentation. I'd like to make some acknowledgments. We have a great staff here, our professors, Dr. Haven, Dr. Fabian, Dr. Wright's new on our staff. He was a great help with our trying to quell our radiative losses or solar losses. Also, Dr. Haslam, Professor Zwick, and then a couple of our other members of the student base. Jenna Humble from Strava Designs, Eric Brown, the second best but most productive welder on campus, and Max Lincoln for the glitter spray paint. And that concludes our presentation. I'll now open the floor to any questions.
difficulties that many before you have gone through to try to make a Stirling engine work with solar. So with that in mind, it's too bad that you couldn't produce some of the parts that you needed for the engine. I would have liked to have seen how successful your head design would have been. A couple questions, and one is, why did you choose it for now?
I'll pass that on to Natalie or Solely.
All right, so a big thing with the Fresnel lens was going into detail. We thought that most of our manufacturing time would have to go to the Stirling engine. So in feasibility of having a solar collector pre-made ready for us and could reach really high temperatures, we chose the spot Fresnel lens. Originally, we had acquired a linear Fresnel lens in prelim, and we did take it outside to test it, and we can even burn paper. So doing more research, we found that there was another Fresnel lens, spot Fresnel lens, and we decided to take that upon us and focus more on the engine and the generator.
Because most of your strokes you use, as you pointed out, focus gear and technical engine. And I guess you understood the limitations associated with using Fresnel and trying to get the energy pointed at one spot. Another question, I guess, is in your head design, did you try to use any heat transfer coefficient calculations associated with that design using aluminum versus what you ended up with?
For our heater, we didn't explore aluminum for the material, although it has a much better thermal conductivity. we felt that some of the temperatures we could be experiencing might not be enough to melt it, but would be enough to warp surfaces and create leaks with gaskets. So we went with steel just because of its robustness, as far as taking the temperatures that we were expecting to see. In our preliminary design, we did use ANSYS to perform thermal analysis to it. Actually, we have these slides in the, do we have them?
These slides are in here.
Can we pull those up real quick? So we did take a previous iteration of this that didn't have the thermal wells on it and applied some constraints within ANSYS, pretty much saying that this surface is insulated and then our inner chamber is where all the heat is coming. Well, sorry, the outer surface is where all our heat is coming from, and then extending into the cylinder. But we were able to find some rather interesting patterns that happen as far as the shape of where the transfer passage is. We have a couple of these, or is it just this one for the?
I think for the heater, it's just, we have one.
Okay. Yeah, we did have a lot more thermal analysis for the cooler, but again, like I said earlier, the reason we went with steel is just for the fact that we felt that it wouldn't warp and open up a leak. One of the previous projects that we found from Worcester Polytechnic Institute, I believe was the name, they used a different motor base for it, but they had a lot of issues with just being able to seal the head. Granted, they used RTP for a head gasket, so I could understand why it didn't want to seal very well. We just didn't want to have that issue at all. We wanted to be able to keep all the energy we could within the engine.
One other question here, and that's on your generator itself. The generator was pretty large for the application, so you're operating on the lower end of the curve, right?
Correct.
So did you see any limitations based on that, like friction, etc.?
We didn't have a lot of options as far as what's out there on a small scale that would produce the 100 watts. The few different options that we did look at were either much larger than this and would take a lot more friction and a lot more energy to turn itself, or just wouldn't be able to produce the 100 watts within the RPM range that we expected to see based on the operating limits of the engine itself and then the availability of gear ratios to
Comment about passing on, and that's your safety matrix, hazard analysis and stuff like. Thought that was very good, and very important, obviously, for your testing.
Well, for your presentation, and you have your struggles with each product. You always happens as much as you can, though. Because sometimes there's nothing you can do about it. That does happen. So I only have a few quick questions. Slide 8. So how do things like clouds, humidity, other environmental factors, how do those affect?
I'll take the question. So this slide is the very, absolute basic.
Okay.
Basically what goes into calculating Qn is you have your rotations and everything about the Earth. And then the second part of the calculation is actually everything in history. So your cloudiness, there's solar radiation that hits the Earth every day. There's other calculations. I think I do have it in the appendices if you want to see a little bit of what goes into the calculation. But it's a two-part calculation that can't be easily, explained or shown clearly. Does that answer your question?
Yeah.
Many of those factors, it's pretty much just an efficiency factor. So we have what we expect, and then we know it's cloudy, or there's a dust storm, it's really windy today too, and well, it might rain in Tucson tomorrow, or something like that. All these go into kind of a factor matrix that come out with a value of from 0 to 1 that's then multiplied to our expectations and kind of build down what we're actually expecting to see.
Okay, so is it more of an approximation?
Yeah, because of because of the large scale of the atmosphere, there's so many factors going in that we can't account for on a moment-to-moment basis. So it's broad and for the most part pretty conservative.
Yeah, I was just kind of curious how you guys were going to predict your theoretical values. That's hard. So
Even just measuring the actual values is just as hard.
it's much more.
Like I said, keeping the tracking alone, like some of our solar testing with the steel block, it moves a quarter degree an hour or a quarter degree a minute. That doesn't seem like much, but by the time you turn around and write your values down, it's no longer on the block. You've burned your tests. You burnt the whole test down, and you got to stop testing. So that's why a lot of our solar testing was rather inconclusive, just with the difficulty of trying to track a sun manually, with two separate components of that too, not just one.
Would an aperture be useful to facilitate that? Because that was something I was kind of wondering, because you talked about manual moving it, and you're thinking, well, that'd be project itself, making aperture.
An aperture was considered for a couple of different reasons, kind of to throttle the engine, reduce some of the heat energy. The issue with doing that is you usually end up having to either put that aperture directly on the head, so it has to withstand the maximum temperatures, or it has to be rather large to restrict the light at the lens itself. But mainly, if you move that focal distance, the distance between the lens and the head itself, you reduce the amount of energy just in doing that. And it added a whole new level of complexity that our budget and time and everything else just it wouldn't allow for, but it was something that was brought up and considered. Similar to this can design, this is something Dr. Wright had expressed to us. If we were to do sort of a blockade, a can of sorts with an aperture on it, we'd be able to throttle, and then we also remove any convective losses from just a crosswind. Through that, you would be able to possibly make a vacuum chamber in there where you have almost zero convective losses within that chamber. And then you can add coatings to here. You can do all sorts of stuff, and if we had $1 million, this would be an awesome engine, but we didn't. So this is what we have.
It's basically a cost for us projects. Slide 16, the only other question I have. I don't know if this is on the slide, but someone mentioned helium, and I was just wondering why helium?
68?
Oh, I heard 60.
Yeah. I was just wondering why is helium as your compressible fluid?
For the working fluid. We didn't, because we didn't expect to ever use helium, we didn't do a lot of research into why that's a more effective working fluid for the system itself. It is a much smaller molecule, and therefore you can pack more of it in a smaller area, so you have the larger propensity to be able to expand that fluid. Again, one of the largest issues with using helium for the working fluid is it's a really small molecule. So, for a standard ring system, it would most likely move past the rings, and then you would just be creating blow-by within the engine.
Yeah, overall, seems like you guys made the best of your situation, which is really good. That's needed a lot of engineering. So you never give them an acting problem.
I don't think there is one, except in all of our textbooks.
That's what I guess.
Excellent job on the problem. Just curious, were you ever able to get the engine to run with your torch and dry ice?
So, continuously, no. There was an interesting phenomenon that did happen. As you can see in that video, I just used an electric drill to spin this, which then spins the motor. So we would pre-cool, we'd throw our dry ice in here, let it get really cold and frosty, and then start preheating this. We did attain a maximum temperature difference of approximately 800 degrees Fahrenheit. So once we were preheated and pre-cooled and we went to start the engine, typically when you rotate this, you feel the compression come up and then it releases, and then the compression comes back and it releases. You feel that in the drill and the kick. But when you initially started, you could get about 3 rotations where you wouldn't feel the kick of compression, and it would actually exceed the speed of the drill for a second and kick the socket. So you could feel it operating like an engine, but after about 3 cycles, we drained the thermal pond that we had on this side of energy, and it just wasn't able to expand the gases fast enough to continuously operate the engine. But through just the feel of that drill, we were able to distinguish that it was operating like an engine, just not for very long.
So if you have a follow-on team, would you recommend they continue to try to make that work, or do you think it's just not suited to work as a sterile engine?
I think that as far as research purposes, this is a great project to discover what a Stirling engine does, how it works, and take some of our recommendations or possibly even just our designs and optimize what's already there and continue on. As far as the success of the engine operating indefinitely, essentially, not continuously for at least an extended period of time, I don't believe now that this engine will be capable of that. I think that the temperature difference that we would need to see in here would exceed the material limitations. This cast cylinder and the aluminum piston in, I believe, would egg out or oval, and you'd be losing too much past the rings. And again, because of the fact that it's just a conventional ring system and probably not even a gapless ring, moving to a different working fluid such as helium may or may not have any effect on it at all.
Okay. Well, good job with the presentation. I like the adaptation of your design to try and figure out how you get some data. One question I do have is based upon the temperatures that you've got, is there any way for you to judge the effectiveness of that regenerator? I mean, that was probably the one component that you had the most control over in terms of your design. And so you did the first, the paper scroll or whatever. That was the design we tried. So what do you think about that regenerator? Do you think it's doing what you designed it to do?
Look at this here.
When we, something that I forgot to mention on our second test is that was, the first test was done with the conventional coil, the second test was done with the spiral coil. So I think in order to compare those two regenerator designs, we would have to do the same test with one coil versus the other. And if we, I think we saw roughly the same, it took about 10 minutes for both of them to heat up to the steady state temperature. And we saw the steady state temperature of the conventional coil was about 400, whereas the temperature of the spiral coil was 700 coming in and then 200 going out. But you can't necessarily compare those because the temperature that we were getting from the conventional coil was when the thermocouple was in contact with either the steel coil or the aluminum tubing of the transfer case. So I think if we're able to do the same test for both of the options, we'd be able to compare and see which one's more effective. I have a feeling we see very similar results because they both take up a good amount of space on the inside, and it'd be interesting to see if the folding and having the effect of having a greater area because it's folded. It'd be interesting to see if that is different versus just a standard folding up with the conventional one. But I have a feeling they'd be mostly similar.
We did just yesterday realize that the university has thermal imaging. So this picture is from about an hour and a half ago. We were out here in the lobby performing a test of it, heating and cooling the respective pistons, and then watching the image. Now this is just a screenshot of the test. And you can actually see from the regenerator at the hot side to the cold side a temperature gradient there. This isn't the best picture. We were able to actually capture a video of this whole process and watch that temperature start to move across the regenerator. And it maintains that gradient. It doesn't heat up the whole side. So we can say that it is effectively pre-cooling and from the other direction preheating the working fluid as it passes through both sides. The video that we have won't be available until most likely after graduation, but it's about a 5-minute video that I intend to compress into 10 seconds and then put on a loop so you can see as it throws heat one direction and cools it going back the direction. And I think it'd be a really interesting infographic to throw in like our thermal power class to show, not exactly that it's heat going back and forth, it's kind of a doctored image, but essentially what's happening as far as the operation of the regenerator. But key point here is you can see in this picture a temperature gradient, which is exactly what you need across your generator to increase the efficiency overall of the system.
A follow-up question to that. Did you get enough temperatures that you could go back to your estimate of what the RPM needed to be and what the predicted power output would be if I had a certain input, to just see what it would have given me in terms of power?
So those inputs, mainly and pressure, obviously that's inside the cylinder, but the temperatures are also internal to the cylinder. The temperatures that we're able to attain with the auxiliary instrumentation that we use are only external temperatures. The thermocouples actually extend into another thermal wall here, so they're not into the cylinder, but they're really close to that cylinder wall. So that's more indicative of the temperatures that we're seeing within the cylinder. Now we could take the temperatures and put it into our MATLAB code and just see what it looks like, and if that is anything similar or close to what we saw for the operation or non-operation of the engine. But I think that those values are going to be greatly skewed, so it wouldn't actually be an indication of what's happening across the site.
Well, thank you very much. Good project.
Although I'm in the front row, I'm not a panelist, so I don't have any further questions. I'd just like to thank the panelists and say you guys did a great job. Thank you.
Were there any questions from the audience, criticisms? Anything? Please don't throw tomatoes until we move the equipment. No? Awesome. Well, thank you so much. And I also want to acknowledge Jan. She's who's been doing our closed captioning. I couldn't look at it too much. I might confuse their words. But I wanted to thank you so much for aiding our presentation. And Aaron for aiding Jan. Thank you so much, everyone.
You're right, you have to stop talking.